first one was in Cambridge in 2019, the Gaia Treasure Hunt. Then there was a training school in Spain, in Barcelona, Milky Way size galaxy formation and high performance computing in 2020. Then we moved on to online, the completely online workshop, the Galactic Center and the Inner Galaxy in Heidelberg, virtually in Heidelberg in 2021. And star clusters, the Gaia Revolution, that WG1 and 2 in Barcelona in 2021. And there are also a few upcoming WG1 related workshops that may be of interest to you. One is coming up in mid-September in Naples, Stellar Evolution Across the HR Diagram with Gaia. The other one is related to stuff beyond the Milky Way, Gaia Beyond the Milky Way, and it's going to be held in Athens end of September. And star formation, which is going to be it's still to be announced when it's going to be held. You can find information about all this in the link I show you here, and you can find information about other workshops and schools that are held by the Cost Action. So moving on to the main part of the talk, how can we study the Milky Way? We are inside the Milky Way, so mapping it and understanding its structure requires knowledge of distances to stars. Observations are obscured by dust, so using only optical wavelengths, as I just showed you a couple of pictures before, does not allow us to see to the into the inner parts, through to the inner parts of the galaxy. So we need ways to measure distances, for example, Gaia parallaxes. We need measurement of space motion of stars so we can understand the kinematics and dynamics. For that, we use proper motions and radial velocities, which are the two components of the velocity, tangential and radial. Both can come from Gaia, especially the proper motions. Radial velocities come complementarily. There's a complement to that from the large spectroscopic surveys. I'll come back to that later. We need ages and abundances to study star formation history and evolution. And that can come from Gaia photometry and medium resolution spectroscopy and synergies with spectroscopic surveys. And all these must be complemented with multi-wavelength measurements, particularly infrared, to let us see through the dust. So all these together can give us all the tools we need to understand our galaxy. I'm showing here a well-known picture that gives you an idea of the revolution that has been really implemented with the Gaia data. The little circle you see here, I don't know if you can see my, let me see, my cursor. Can you see my cursor?
Yeah.
Yeah, okay. So until Gaia, we could have 10% accuracy in stellar distances only in the inner 100 parsecs around the sun. Now the 10% accuracy is extended to 10 kiloparsecs around the sun, past the center of the sun, and approximately 1 kilometer per second proper motion accuracy out to 20,000 parsecs away. So it's a big revolution in terms of distances and accuracies in proper motions across the Milky Way, but also in the surroundings of the Milky Way. As you'll see later, we can measure proper motions of tens of satellites to the Milky Way using the Gaia data. And this is really fantastic. So synergies are very important, especially with spectroscopic surveys, as will also become apparent later, because radial velocities and metallicities are very important in order to draw a complete picture of the various components of the galaxy, and the Gaia data for that are limited to very bright objects. So it's very important to use other surveys, spectroscopic surveys of the Milky Way. And I just show you a few of those: Apogee, RAVE, LAMOST, GES, and Gala. And there are various others that are planned. You can see a review, if you wish, by Yan et al. To 2022 for all the surveys that are going on of galactic stars, providing metal abundances and accurate radial velocities. So let's see what we get from Gaia. What we get from Gaia, first of all, is astrometry. That's the basic, the key mission of Gaia, to provide astrometric data, accurate astrometric data for millions of stars in the galaxy and nearby objects. What it provides is 5 components of the phase space. So 2 for position, 1 for parallax, and 2 for proper motion, PMRA and PMDEC. And these 5 components are provided for millions of stars. We all know what parallax is. I just put a cartoon here to remind everyone. And the proper motion is a tangential velocity composed of two parts, the proper PMRA and PMDEC. And this is the proper motion angle that we measure, really. And in order to transform it into actual velocity, tangential velocity, you also need the distance, which is provided by the parallax. So I show you here some well-known plots that indicate the accuracy that is achieved at the moment with the Gaia data in terms of parallax. This is the standard uncertainty in parallax on the perpendicular axis versus G magnitude. I'll explain in a bit what the G magnitude is. And expectedly, of course, for fainter stars, the uncertainty is higher. And what you see here on the right-hand side are plots showing the distribution of the standard deviation for positions, proper motions, and parallax in the sky, on sky plots, which really have to do with the way that Gaia measures and how many repetitions have been achieved in each part of the sky. So for the moment, you can see that the accuracy, the distribution of the accuracy is very inhomogeneous. The second important aspect of the Gaia data are spectrophotometry. So there are 2 photometers, let's say, that use two prisms, one in the blue part of the spectrum, one in the red part of the spectrum, and jointly they give you this spectra that you can see put together here in the bottom plot. These are spectra from the blue low resolution spectrograph, and these are spectra from the red low resolution spectrograph for different stars of different temperatures. And you can see the temperature coloring here. The red ones are cool stars, the blue ones are hotter stars. And using these SEDs, these energy distributions, and applying these distributions of the filters, we can also get magnitudes. So BP, RP are the blue and red magnitudes, and G is the G magnitude that encompasses most of the range of the 2 other filters. So these BP, RP, and G magnitudes allow us to construct color magnitude diagrams, while the spectra themselves allow us to derive stellar parameters from fits to the observed low resolution, to these low resolution spectra. An example of a color magnitude diagram that can be constructed using G and BP minus RP is this diagram of LMC stars. The Large Magellanic Cloud is one of the closest galaxies to our own at around 52 kiloparsecs. It's a disturber for our own galaxy. It interacts with our own galaxy and with its companion, the Small Magellanic Cloud. And you see the density distribution of stars in this picture here, and the CM diagram, which shows amazing detail in the various stages of stellar evolution. It's really a textbook plot. I wish I could spend more time discussing this. As I said, apart from Kalman-Manchu diagrams, one can also derive astrophysical parameters. These have not yet been released for a lot of stars, so data release 3 is going to provide astrophysical parameters for many more stars than DR2. And you can see here an example of parameters, the temperature and absolute magnitude, derived, of course, from the apparent magnitude together with the parallax information. And in the bottom, you can see in these 4 plots examples of the effect of temperature, metallicity, for example, log G, and absorption for various types of stars. And using all this information, one can derive T effective log G, M over H, and AG for the stars studied. So this is just an overview of what can be done with the low resolution spectra. Apart from the low resolution data, there is also medium resolution spectroscopy, the radial velocity spectrometer as it is called, that produces high resolution spectra for brighter stars, of course, from which you can get radial velocities, of course, and also metal abundances. And this is an example of a spectrum with some the basic metals that can be measured in it to provide abundances for all these different elements. And on the right, you can see an estimate of the distribution of Gaia sources with radial velocities on an XY plane. So this is an overview. I don't expect you to read all this, just to show you with the Gaia data release 3, there's going to be a huge improvement on the number of stars for which we have information radial velocities, spectra, which didn't exist at all in the previous data releases, radial velocity spectra, BPRP spectra, variable source classifications, and so on. So all these will come in less than a month. So we're all looking forward to that. What can we learn from Gaia data and synergy with various spectroscopic surveys about the structural components of the galaxy, which is, of course, the focus of WG1. I show you here an infrared picture of our galaxy so that we'll be able to see through the dust and be able to see the bulge and bar region here as well. So the galaxy consists of the disk, which is this feature here, the bulge and bar in the center, and the halo which surrounds all these features and is very, very extended. So the scales are more or less written here, 30 kiloparsecs more or less for the disk. The thick disk, I should say, is thicker in the vertical direction, as you can see. It's much smaller in terms of mass than the thin disk. We'll talk about it a bit later. The dust and the young stars and gas are basically distributed in the thin disk. I'm going to try and go through all the basic components with what we've learned about these components from the Gaia data. This is the location of the sun with respect to the various components of the galaxy. So, the disk. The disk I showed before has a total mass of about 6 × 10⁻¹⁰ solar masses. Most of it is in stars, so 95% of the mass is in stars. It has a thickness of about 350 parsecs. And it has stars from newborn to very old. Actually, using the Gaia data, parallaxes for distances and Kalman-Manchu diagrams, one can derive a quite accurate star formation history for the disk. And we'll see that later if there is time. The thick disk is much smaller in terms of mass. Only 5% of the stars of the disk are in the thick disk. Is thicker by about ×3 with respect to the thin disk, and hotter in the sense that it has slower rotation and higher random motion. Generally has stars older than the oldest thin disk and generally of lower abundance. So there are significant chemodynamical differences between the thin and thick disks, and these have been confirmed and extended with the Gaia data. We know, of course, that the disk is rotating. Most of the stars are in almost circular orbits, and there are spiral arms, characteristic of all spiral galaxies, of course, in the disk. There are it seems 4 main spiral arms and 1 broken, and data from DR2 and DR3 have been used to analyze these spiral arms, find them and analyze them in detail. For example, in a paper of 2020, Koperskov et al. Discovered or basically analyzed in detail the presence of 4 spiral arms in more or less the solar neighborhood. So just to show you how you can measure these things, imagine that the sun is here in this location here, and this is our line of sight across the galaxy towards the center of the galaxy, above the center of the galaxy. And let's assume that we are crossing different spiral arms along this line of sight by measuring velocities, for example, at the different locations where you have overdensities. You can find different spiral arms and locate them along the line of sight. This is very brief, of course, but there's no time for longer explanations. Here you can see another work which used the density of upper main sequence very young stars and open clusters in the solar neighborhood. And as you can see here, these densities, over densities, have a very patchy distribution, but coherent along these lines that seem to be parts of segments of spiral arms. This is work that was published by Poggi et al. In 2021. This also is related to spiral arm features near the solar neighborhood. And it was discovered using Gaia data, EDR3 data. A very exciting result that came out from Gaia data is the so-called Gaia phase spiral. This is different from the spiral arms that we saw before. It appears on diagrams of Z, which is the vertical distance from the disk, that's along the horizontal axis, and radial velocity along this perpendicular direction, Vz. And the color has to do with V phi, the azimuthal velocity. And you can see there is this spiral arm that is revealed, and this was already seen with the Gaia DR2 data. It's a fascinating result that apparently is relatively easily explained. I'll try and explain very fast. What it shows you basically is perpendicular oscillations of stars perpendicular to the disk. And you have different periods of oscillation at different distances across the disk. And as the disk rotates, you get the warping of the shorter period faster than the longer period outer regions. And so you end up with this phase mixing that looks like a spiral that I showed you before. This has been shown also with n-body simulations and basic theoretical approaches, and it seems to work pretty well. The question is, what is creating this disturbance perpendicular to the disk? And one of the, let's say, most accepted explanations is that the perturbation is due to a satellite that is going around the Milky Way and perturbs the Milky Way disk. And this is the Sagittarius dwarf galaxy. And it has been shown again in simulations that it can indeed create this sort of effect, as you can see in this in the bottom plots here. There are other possibilities that have been discussed. For example, the bulge buckling, but I don't have time to go into that. Using the BPRP and G magnitudes and parallaxes to transform the apparent to absolute magnitudes, we get this beautiful CMD column magnitude diagram for the solar neighborhood within 100 parsecs from the sun, and analyzing that together with stellar evolution models and evolutionary tracks, we can get information about the star formation history of the solar neighborhood. It's important to note that most of the star formation activity happened about 10 gigayears ago, followed by a decrease in star formation with a minimum around 8 gigayears ago, and then there is an increase again about 5 gigayears ago, and so on. And some of these may be related to accretion events, perhaps, or changes due to interactions with other galaxies. This is an example. Again, for the Sagittarius galaxy, it has been proposed that there is star formation activity related to close passages of Sagittarius. How much longer do I have?
Well, you're almost out of time. So.
Okay. So I'll go on to show you some very significant results on the stellar halo that also came up from Gaia, and it was shown again from Gaia data together with apogee spectroscopic survey data that there is a major component in the stellar halo that is the remnant of a giant merger with a galaxy called Sausage Enceladus that happened, this merger, about 10 gigayears ago. And this is something that also was discovered basically using the Gaia data. It was a revolution for our understanding of the Milky Way galaxy. Here you see stellar streams that have been found also using Gaia data together with other spectroscopic data that are remnants, that are tails of various objects like globular clusters, mainly globular clusters or dwarf galaxies that are being disrupted during their movement around the galaxy. And to end my talk, I would like to show you a recent result based on an idea that was expressed a long time ago about hypervelocity stars. We cannot see with Gaia the center of the galaxy, but we can see the effects of what happens when a binary star comes very close to the central black hole. What can happen is that one of the stars ends up going around the black hole and the other star gets ejected at a very, very high velocity. And one such star, hypervelocity star, has been discovered recently using Gaia and AAT data. And this is described in a paper by Kopasov et al. In 2019. So even the center of the galaxy that is not really visible, it's hidden by dust and so on, we can still get some information about it from the Gaia data. We also get a lot of information about the surroundings of the Milky Way, as I said at the beginning. There are measurements now, 3D velocities of 46 dwarf galaxies by Lee et al. In 2021, and a total of 74 dwarf galaxies, proper motions by Battaglia et al. 2021. And this is a major step forward towards understanding the dynamics and evolution of the local system, the local group of galaxies. Thank you very much. Sorry, I had lots more to show you, but there's no time. So, any questions?
Well, Despina, thank you for a really, really interesting talk, and almost every study that you mentioned actually told about something very inspiring and very new about Milky Way. So are there any questions, please? Do we have any questions or on site or online?
The chat, maybe.
In the chat, no, I don't see anything in the chat. Yeah, okay. So, I would like to ask a very general question, like in the context of 2013, when like epoch, pre-Gaia epoch, all right. So, is Gaia fulfilling expectations? Do you find it inspiring?
I think it is actually. I think there has been a revolution in our understanding of the galaxy and also the local group. I work a lot on the Magellanic Clouds, and the understanding that we have now of the Magellanic system is unprecedented. And also absolutely of the galaxy. I mean, all the accretion history of the galaxy was only hinted upon by previous spectroscopic surveys, and was only made really possible by the proper motions and parallaxes of the Gaia mission. Also, I guess you'll hear from the next speakers, there's been a lot of great results on stellar evolution and other aspects of astronomy and astrophysics coming from the Gaia data. But I'll let Gisela talk to you about this later.
I see one. Thank you for the answer. I see one question from Paula. Paula, can you unmute yourself and ask the question?
No. She must ask to the chat.
Sorry, I can't hear you.
Paula, you should write in the chat, I think, the question. Yeah, so for the guests, apparently the microphone is disabled. Yeah, so if you would write in the chat.
Where is that question? My mic is disabled.
Yeah, well, wait.
Okay, yeah. She says it's a comment only, so I don't know if she's going to write it or not.
All right. Yes.
Yes, I agree. Yeah, yeah. We're all waiting and expecting DR3. Yeah, indeed.
Yes, so DR3 will come quite soon.
Yeah, in less than a month. Yeah,
As,
3 weeks. 3 weeks. Yeah.